everybody, and welcome to Echo Live. My name is Anna, coming to you from the Michigan Science Center's Echo Distance Learning Program. Today we are talking all about reaction rates. I see lots of our friends starting to chime in the chat or the comments feature, introducing themselves. Thank you all so much for doing so. You know the drill by now. If you haven't done so already, go ahead, say hello, introduce yourself in the chat, practice using that chat feature to communicate with me all throughout the program. I am keeping an eye on the Facebook comments, our chat feature in Zoom, and on YouTube as well. So don't worry, I see all of you, I hear all of you, and I'm hoping that you can use the chat feature today to learn with me all about reaction rates. Now, the first thing I would like to ask of you out in the comments is I'm looking for a solution to a problem that I have here in the Echo Studio. Now, I poured myself this glass of tea, and if I'm being honest, I don't really like tea almost at all. The only way that I will drink tea is if I pour a whole ton of sugar into it, making it pretty sweet. I know that's not super great for you, but it's the only way that I'll drink it. Now, my question for you is, what would be the fastest way for me to sweeten my tea using the sugar that I have here? So if I zoom in on my tea here, you'll notice that when I poured the sugar into the tea, it kind of sinks down into the bottom there. So maybe that wasn't the best solution, but what I'm wondering from you is, can you help me out with a solution to this problem? What would be the fastest way to sweeten my entire tea, not just the layer at the very, very bottom here, where you can see that the sugar is sitting? Now, it's important to remember, right, that if I left this tea here all day, just how it is right now, that over time, diffusion would sweeten the entire glass of tea. The sugar molecules would go through the process of diffusion, which tells us that they want to move from an area of high concentration, where there's a lot of sugar molecules, to an area of low concentration, where there are less sugar molecules. So over time, right, over many, many hours, diffusion would cause those sugar molecules sitting on the bottom of the glass to move upwards towards that area of low concentration, until eventually the entire glass of tea is equally saturated with sugar molecules, creating what we call, again, one of those homogeneous mixtures. But that would take a very long time, right? That would take a very long time for it to be completely evenly mixed. So let's see, what did you come up with in terms of solutions for me? Anyone think of what would be the fastest way? What could I do, or what could I add in order to mix that sugar into the glass and make it very, very sweet? So even if let's see, if I poured in more sugar, maybe that would help. But I'm getting the same results here. Even though now I've added more sugar, it's just sinking all the way down to the bottom of the glass. Some people are suggesting other things that I could add like honey, but not really helping me with my homogeneous mixture here, right? I still have tea on top, sugar on the very, very bottom. One thing that I could think of, right, is that I could stir my solution here. By stirring, right, I am adding energy into this solution, causing those sugar molecules to diffuse more quickly. I could also consider heating up our solution. We talked about this on a past episode of Echo Live, where we talked about molecules in a warm solution move much more quickly, right? They have a lot more kinetic energy, that energy of motion. And so if I were to heat up this tea, the molecules would dissolve in it much more quickly. Both of these are examples of ways that we have sped up this reaction, ways we've pushed it to completion. But this is an example of a physical change. Physical change meaning that we started and stopped with the same ingredients or same molecules. At the beginning, we had tea and sugar. And at the end, we had tea and sugar, just mixed in a bit more evenly, spread out over the amount of space inside my glass. That's a physical reaction. For the rest of the show, we're going to talk about chemical reactions, where we are going to combine different atoms and molecules together, cause them to break apart, rearrange, and reform into new products. So that is a chemical change where what we start with is different in terms of its chemical composition than what we are going to end with. Now, we are going to do a bunch of chemistry here inside the studio today, which means that we need to practice good lab safety. Of course, I have safety equipment that I'm going to be wearing or using throughout the program. I've got on my handy dandy lab coat. I've got my safety glasses, which I'm going to pop on right now, and I'll just leave them on for the rest of the program. And I also have some nitrile gloves to protect my hands, just in case any of the ingredients or chemicals we're working with today are harmful. But unfortunately, there is another steadfast, unbreakable rule in a chemistry lab, which is you are never, ever allowed to eat or drink in the lab. So even though we did a kind of cool physical reaction here with my tea and sugar, I am not going to drink these, which is fine with me because, like I said, I don't really like tea anyway. But a general rule for any time you are doing a chemistry experiment is you never want to eat or drink in the lab, even though these are food safe, even though there's nothing wrong with them. I may have touched something, I may have contaminated these, which could make them toxic or dangerous. And so I'm just going to go ahead, remove those from the table, and those are no longer edible. That is now science tea. It is not drinking tea. All right, so let's understand a chemical reaction a bit more, and what exactly do we mean by a reaction rate? A reaction rate is how fast a reaction goes, how quickly it can turn from reactants into products, from start to finish. And we need to understand something called collision theory to truly understand what makes a chemical reaction and not a physical one. Collision theory tells us that atoms and molecules are constantly colliding. But in order to have a chemical reaction where we take two different ingredients like A and BX to turn them into something like B and AX, they need to collide and follow a few different factors. Now, molecules are colliding or hitting each other all the time because atoms and molecules are constantly moving, even if they're moving very slowly, like in something like a solid. They're constantly striking each other, but most of the time we have what we call an ineffective collision. This means that even though these two molecules, A and BX, hit each other or collided, we didn't actually have any reaction take place. We didn't form the products that we're looking for. So we have an empty side of our diagram over here. In an effective collision, A collides with BX and forms these different products. That's an effective collision. And there are two major things that have to happen in order to have an effective collision. Number one, these reactants have to have enough energy when they strike each other. They have to hit each other fast enough that a reaction can take place, that they can actually have enough energy to break apart, reform, and then form the products. They also have to strike each other in the right spot. So if you notice in our top diagram, A struck B, but for an effective collision to take place in this reaction that we have noted here, A has to strike the X atom on this molecule here. So collisions are happening all the time. And what we're going to talk about today is how we can increase the rate of a reaction. That means that we'll be getting more or faster effective collisions that force our reactions to go to completion and form products. Now, the first way that we can speed up the reaction rate of a reaction is by changing the temperature or by changing the overall amount of kinetic energy. We said that kinetic energy is motion, right? And we've talked about our states of matter a whole lot here on Echo Live. We know that by adding thermal energy or heat to a substance or to a reaction, we give those molecules more speed. They start to move more quickly, which could give us more collisions or faster collisions or more likelihood that they'll collide in the right spot. The best way I know to show this is a reaction using glow sticks. We've talked about glow sticks during our luminescence episode of Echo Live. You might remember that I took apart this little glow stick here and I very carefully deconstructed it. This is something that you should never try at home because inside the outer plastic tube of any glow stick is another tube that's made of glass. You can see that there is a liquid inside this glass that is hydrogen peroxide. And when you crack a glow stick, when you bend it and you hear that cracking noise, you are breaking the glass tube inside, which releases the peroxide into the chemical surrounding it, which starts off that chemical reaction, just like in that diagram we just talked about. So I've got two glow sticks here, and we are going to manipulate the speed of these reactions by using temperature, by either adding or taking away thermal energy from these reactions. So we'll go ahead and we'll crack our glow sticks here. See if you can hear that cracking noise. Again, that's that glass breaking inside, releasing that peroxide into the surrounding molecule. And look at that, I have a dud glow stick, but don't worry, I have more. We are going to grab another glow stick. I'd like to make sure we grab the same size or the same color. That way we don't have any variables in our reaction other than the temperature. How is it possible that I have two dud glow sticks? Man, oh man. Fun fact, glow sticks are pretty inexpensive, but the blue is actually the hardest color for scientists to make. It actually is the least cost effective, which is why in some packs of glow sticks, you'll find the least number of blue glow sticks. It just has to do with the chemicals that go into producing this specific wavelength of blue light. It's a little bit harder to make in a lab, which is why sometimes you'll have less blue glow sticks in a variety pack like this one. Now I've got two graduated cylinders or Erlenmeyer flasks full of water here. This one over here, this one is hot water. This one right here, you can see that the glass is kind of steamed up or fogged up. That one is really, really cold water. And I'm going to go ahead and drop a glow stick down in each of those glasses. Now, it's kind of difficult to see the reaction taking place because it's pretty bright here in the studio, but I'm going to help us out. I'm going to go take away some of the lights by just kind of coming over here. I'm going to turn off one set of lights and our second set of lights. Now, tell me in the chat, what do you notice? What is the difference between our glow stick in the hot water, which is this one right here, and the glow stick in the cold water, which is this kind of foggy steamed up glass? Even if I remove the steam, you should notice a big difference between our two reactions. What is the difference? Tell me in the chat, and you'll notice the longer they stay in their different temperature water, the greater the difference becomes, the more noticeable the difference between these two reactions. Nancy tells us that the hot glow stick is glowing a lot brighter. Tell me whether you agree or disagree, or do you notice anything else going on in these two reactions? Remember, the only variable that we changed is the temperature of the environment. It's the same type of glow stick, it's the same color glow stick, it's the same amount of water, the same size glass, but one is in hot water and one is in cold water. Yeah, Helena tells us that cold is fading away. Yeah, everyone's kind of coming to the same conclusions here. That's great. I'm gonna go ahead and turn my lights back on here inside the studio, and let's talk about why that is. Now, in the hot glass, right, that glow stick is glowing much brighter because that reaction is going more quickly. We said that by speeding up the molecules in that reaction, just by adding kinetic energy, we're pushing that reaction to completion. This glow stick will glow much, much brighter because one of the products or byproducts of a chemical reaction in a glow stick is light. That's really the one we care about. Now, there are upsides and downsides to this, right? We said you can try this reaction at home. So if you want to try getting your glow stick to glow very, very brightly, you can drop it down in a glass of hot water. But you can also try putting your glow stick in something like the freezer. And by doing that, by slowing down the reaction, you'll notice that this glow stick is going to last much, much longer. Because we've taken away some of the speed of those molecules, we've reduced the number of effective collisions, right? And so this glow stick, even though it's not as bright, will last much longer. Whereas on the other hand, the hot glow stick will glow very, very brightly, but eventually over time, it will use up all of its reactants and stop glowing pretty quickly. It's So pros and cons to either way. You can try this at home, but one thing I do have to say is you should never, ever put a glow stick in the microwave. We talked about microwaves here on Echo Live. We know that things can explode when they go in the microwave. We also talked about that the insides of a glow stick can be toxic and hazardous. So we never want to open up a glow stick at home, and we never want to put them inside the microwave. All right. So we've talked about one way to speed up our chemical reactions or to affect our reaction rate is by temperature. The next one we're going to talk about is surface area. So I have on this tray, I'm actually going to take things off the tray because I want you to notice the color of the solution inside these two beakers. Now, the two beakers right now are full of the same solution. This is a solution of potassium permanganate. Potassium permanganate is pink in the presence of an acid. So this is a slightly acidic solution of potassium permanganate. Now, we also have two radishes here. So I've got one radish here that I've just kind of peeled like a potato. And then I have another radish that I've chopped up into tiny little pieces. They started off the exact same size, but I want you to tell me which radish, the whole radish or the chopped radish, which one has the greatest surface area? So think about it. I'll give you kind of a 360-degree view of this radish. Is the whole radish or the chopped up radish the one with the greater or larger surface area? What we're going to be doing is we are going to be dropping our radishes in their own solution of potassium permanganate. Now, radishes are full of something called malic acid. Malic acid is an acid, but when it reacts with potassium permanganate, it begins to oxidize. It begins to be reduced, meaning it loses its acidic properties. And so over time, our radishes will react with the potassium permanganate and turn this solution colorless or clear. And a lot of us are now starting to chime in the chat, telling us that you guys are exactly right. This radish that's chopped up has a much larger surface area than the whole radish. Because I've sliced it into tiny pieces, each one has its own surface area. And by chopping it into many, many pieces, the surface area of this is much, much greater. So we're going to put the whole radish in this beaker. And we actually don't need the stirring rod because I can just stir with the radish itself. And then into this beaker, I'm going to add our chopped up radish. Now, we are going to stir, and we're going to look for a color change. And you can give me a hypothesis in the chat based on the surface area of our radishes here. Which one do you think is going to generate a colorless solution more quickly? So we said that the chopped up one has a greater surface area, which is exactly right. And we have a slightly smaller surface area on our whole radish, even though they have the same overall volume and mass. And we're already starting to notice some results, especially if I stop stirring this solution over here. Even after just about 30 seconds of stirring and mixing, our chopped radish solution is almost entirely colorless. That malic acid has been reduced by the potassium permanganate, which removes the pink color from the solution. This one, still working. I don't really need to stir the chopped radish bowl anymore because that one is now colorless. But we can see that surface area, right? Having a greater surface area gives us a higher probability of having effective collisions. This beaker, right, is already gone all the way to completion. Because there's more surface area and more of those malic acid molecules being exposed to the potassium permanganate, this reaction rate is much, much faster than the one with the whole radish. Now I'm just going to keep stirring here, but we don't have to wait all day. We can just leave our whole turnip here in the solution, but it is gradually getting clearer and clearer over time, although not entirely clear still, even though this one We've now been waiting for about double the amount of time as the cup with our chopped radish. So temperature and surface area can both affect the speed or the reaction rate of our reactions. All right, we've got a couple more to go. The next factor we're going to talk about is concentration. And we've talked a lot about density on Echo Live, which is actually very similar to concentration. If you were to think about a chocolate chip cookie, or let's say we had 2 chocolate chip cookies that are the exact same size, but one chocolate chip cookie has 3 chocolate chips, where the other chocolate chip cookie has 30 chocolate chips, we would say that the cookie with more chocolate chips has a higher concentration of chocolate. Even though the area or the amount of cookie is the same, more of the cookie over here is made up of chocolate chips. And so that one has a higher concentration. Now, concentrations of solutions that go into chemical reactions can also affect our reaction speed. In our next experiment, we're going to be combining 2 chemicals. One of them is sodium thiosulfate. The other is hydrochloric acid. Now, on their own, both of these solutions are colorless. Both of these chemicals are clear liquids, but when we combine them together, we form a precipitate, which is a solid. The precipitate that we form is actually sulfur, which is white and it's kind of stinky. And so what we are going to do is combine our chemicals, and we are then going to watch our precipitate form at different rates. I have this one set up under our document camera over here. So let's go ahead and switch our camera. And you'll see that I have our reactions set up. Now, in the 4 beakers that we see here, in A, B, C, and D, we have solutions of our thiosulfate solution, our sodium thiosulfate. One is most concentrated, one is least concentrated, and 2 other ones are somewhere in the middle. I'm not going to tell you which is which just yet. Now, what we're going to do is we are actually going to time these reactions. So let me get out my handy dandy pocket stopwatch, AKA my cell phone. I'm gonna set it right over here. Oh, I hope we'll still be able to see if I angle our camera just a little bit better. Perfect. It's important that we are still going to be able to see the letters of our solution, because what we are timing is from the time we add our hydrochloric acid to the time that we can no longer see the letter at the bottom of the glass. We'll start with solution A, and we said that we are timing, again, as soon as we pour the solution in, we'll hit start on our stopwatch, and then we'll hit stop when we see, when we can no longer see the A in our first beaker here. So 3, 2, 1. Now our solution is going. Oh no, my timer did not start there. Darn gloves. All right, that might skew our results just a little bit, but we've got 3 more to go. So I'm hoping that we still, with 3 more trials, can still see good results. I can turn off the background if that's bothering everybody. That we could still see just fine, but absolutely, I don't mind turning it off at all. Keep an eye on the A inside the glass, because what we are looking for, like we said, is a color change. It's starting to get cloudy. It is starting to fog up after about 30 seconds, but we won't stop the timer until we completely lose sight of the A inside the glass. We are getting there. We're getting there. I'm preparing my finger to hit stop on our stopwatch as soon as we no longer see the A. And we're almost there. I'd say I can still just barely see it, and now it's gone. So it took 58.28 seconds for that solution to precipitate enough sulfur that we could no longer see the A at the bottom of the solution. That was written on the paper underneath the glass. Let's move on to our next beaker, which is solution B. So we'll reset our timer. Remember, our first one, actually, it would be good lab practice for me to write down our results here. So A took us 58.28 seconds. All right, we'll reset our timer, prepare ourselves for solution B. And here we go in 3, 2, 1. Got it that time. Keep in mind that our first reaction, we might need to add just a few more seconds to it because our timer did not start immediately. But now we are timing solution B. As that hydrochloric acid combines with our solution of sodium thiosulfate, it is getting cloudy as we precipitate that sulfur. And it's getting cloudy already much more quickly than solution A. I'm getting prepared to stop our timer and just about now. All right, so in solution B, it took 35.46 seconds. 35.46. I've written right on my piece of paper here. Let's get prepared for the next one. Now tell me in the chat, while we're waiting for this next one to precipitate, which solution do you think had the higher concentration? Was it solution A or solution B? Which one do you think was more concentrated? And we'll talk about how this actually works just after. So go ahead and take a guess for now. Let's go ahead and start reaction C in 3, 2, 1. Thank you, everyone, for recording our data, even there in the chat. That's awesome. I really appreciate it. That is good note keeping, as always. You should definitely be recording data as you go. You don't have to trust me. You can record your own data, which is good science. All right, our C has almost disappeared. And stop. So solution C took even less time. Solution C took only 29.12 seconds in order to disappear that C, become so cloudy that we can no longer see it. All right, let's try our last one, which is reaction D. So let's go ahead and start this one in 3, 2, 1. And we are waiting for our precipitate to form. Once that D disappears, we'll stop our reaction, or we'll stop our timer, and then we'll talk about our results. And it's getting pretty cloudy, pretty cloudy, pretty cloudy, and the D is gone. Now D went the fastest at 22.52 seconds. So let's think about these reactions, and let's think about collision theory. Let me go ahead and turn my camera back to our studio cam here. Ooh, look how funny my phone looks just like that. All right. Ta-da! Oh, man. Hold on one moment, guys. That looks pretty cool. I think I look almost like a superhero. Virtual background. Ta-da! Technical glitches, always fun here on Echo Live. But let's talk about the results of our experiment. Thank you, everyone who's been recording some notes down there in the chat. It is super helpful. If you need me to remind you of those numbers one more time, we were recording the amount of time it took from the start of our reaction to what we are considering the stop of the reaction when we formed enough precipitate to completely cloud the glass. Reaction A took 58.28 seconds. Reaction B took 35.46 seconds. Reaction C took 29.12 seconds. And reaction D took 22.52 seconds. So they got faster and faster and faster as they went. Based on that data, which of our beakers, which solution did you think had the highest concentration of sodium thiosulfate? Now think about collision theory, right? We said that we're getting collisions all the time, but we can do things to affect the number of effective collisions. We can get more effective solutions, right? By using either a greater or a lesser concentration. Now you guys are getting it. You are exactly right that the highest concentration solution was solution D, the one that went the fastest. Since it had the most amount of sodium thiosulfate molecules in it, there was a higher chance that it would collide with our hydrochloric acid, form that precipitate, and those reactions went much more quickly. So the three factors that we've talked about so far, right, have been temperature, surface area, and concentration. By increasing temperature, increasing surface area, or increasing concentration of your reagents, you can have your reaction rate will increase. It will speed up and your reaction will go to completion much more quickly. Now we've got one last reaction to show off. This one is one of my favorite classic science experiments that we call the iodine clock. Now in this reaction, there are actually two chemical reactions taking place at the same time. One of them goes much more quickly or has a higher reaction rate than the other. Since both reactions are going on at the same time, we get some pretty interesting results. Now I have two solutions here. Solution A, this very clear, not cloudy solution, this is a solution of iodine and vitamin C. And the one solution B, the slightly cloudy looking one, this is a solution of liquid starch and hydrogen peroxide. What we are looking for here is the color change that happens when iodine goes through its different forms. Iodine exists in a few different forms. If you've ever had iodine put on you at the doctor's office, either before a surgery or maybe an incision or a shot, we know that it's normally kind of this orangey dark brown color, and it can actually stain your skin, which is okay. It's only temporary. But normally iodine solutions are brown. But in this solution, we said we had iodine, but it is certainly a clear solution. That's because iodine is colorless when it reacts with vitamin C. The vitamin C will actually consume the ion of iodine, turning it back to a different form of iodine, which we see as colorless. And then over here, we don't have any iodine, but we have a solution of starch, which is why that one is pretty cloudy. But when we combine these, let me show you one more picture. When starch is combined with iodine, we get this very, very dark blue solution. So we can have colorless iodine, we can have brown or orange iodine, or we can have blue iodine, depending on the state that that iodine ion is in. Now, we are going to combine our two solutions here just by swirling them back and forth. And then we're going to have to wait because we said there are two reactions taking place inside the glass, but one goes more quickly than the other. So let's take a look at this reaction. We'll take solution A, our iodine and vitamin C, and then we're going to pour it into our starch and peroxide. And let's go ahead and take a look at what happens. We're just mixing our solutions back and forth. 3 times should be plenty. And now I'm just going to set it down here on the table. And the most fun part of any experiment, right, is waiting. Right now, we said there are 2 reactions taking place. The vitamin C is consuming the iodine, trying to turn it clear. But at the same time, our starch is combining with the iodine, trying to turn it blue. But the vitamin C reaction is much more favorable. It has a much lower activation rate or energy that it needs in order to take place. And so that reaction has to go through first before our second reaction takes over and we see this color change to dark blue. So reaction rates can affect the results of our experiment. Once the vitamin C was used up, which happens over time, then we were finally allowing the liquid starch to combine with the iodine, which gives us this very, very dark blue, kind of weird color of iodine. Now, if we were to add more vitamin C, of course, we could re-energize this solution, turn it back clear, and so forth, right? By adding or taking away reagents, we can also affect these reactions. Now, this is about the end of our program here, but of course, I'd love to see if you have any questions about our reaction rate episode of Echo Live. While we wait for some questions to come in, now is a great time, of course, to thank the sponsors of Echo Live, like the Ford Motor Company Fund and Denso. They have allowed us to bring you these programs live for free every weekday at 2:30 since quarantine, and we are not done yet. But of course, if you would like to keep learning with us this summer outside of Echo Live, I highly recommend that you sign up for one of our weeks of My Size Spark Camp. These camps are completely virtual, so even if you don't live in Detroit or in Michigan, you can still sign up, do daily science experiments with us with the help of me and some of our other educators, and you'll also get to tune into Echo Live as well. If you'd like to win a free week of Spark Camp, you can still fill out the survey, which has been linked on our last few videos. It's also been posted to our Facebook page. We will be announcing the winner of who is winning the free week of virtual camp on Monday. So you have until Friday to fill out that survey, enter for your chance to win, and we will announce the winner on Monday. Of course, if you don't win the week of My Sci Camp, you can still sign up. I highly recommend it. It's going to be super fun. It's going to be an amazing experience for everybody because unlike our Echo Live programs, we'll actually get to interact with you individually. We'll get to see each other on camera. We'll get to have discussions and try experiments together live in real time. Question that I see in the chat, Becky asked, what would happen if you put a glow stick in the microwave? If you haven't seen our microwave episode of Echo Live, I highly recommend it. Go back and watch, but you'll notice that when you put things in the microwave that don't belong there, it's kind of common that things will explode, which is of course not what we want because once you crack your glow stick, right, there are tiny shards of glass. And since you use your microwave for food, right, I would not recommend doing science in your microwave. We want to keep science and eating very, very separate. That way we're not contaminating any of our food on accident. Steve, you can of course bring your sister to My Sci virtual summer camp. We would love to see you and your sister there. That would be so cool to have even more people joining in on the fun. Our camps are designed for 3rd through 8th grade, but anyone can join in. If you are younger than 3rd grade and still have a passion or an interest in science, we'd love to see you there. We will help you out. Maybe you have an older sibling or parent or adult in your life that would like to help you with some experiments, but these camps are going to be fun for everybody. So with that, that brings us to about the end of our program here today. Thanks everyone so much for joining us for reaction rates. We hope we'll see you back here tomorrow in our